I'll not repeat the introduction. So our motivation was, so actually the goal of this work is pretty similar to the previous talk, except we are taking a slightly different approach. So our motivation also comes from smart contract verification. And yeah, I don't need to talk much about Satora. You all have seen the talk by John earlier. The main thing is that the programs are translated into SMT formulas, and we try to solve that. And the benchmarks we have gotten, we saw that they are using 256-bit unsigned integers, or bit vectors. They are mostly using linear arithmetic and also some nonlinear parts. And there are bitwise and structural operations, but they do not form the majority of the formula. So for example, that's an excerpt of one such a benchmark. Yes, I don't need to go into detail here. So our project is called PolySAT, and it's a new theory solver for bit vector arithmetic. And instead of bit blasting, we base it on modular integer arithmetic. We do not translate to integer arithmetic. Here we use a MCSAT-like approach. I think you only mentioned it briefly. We search for a bit vector assignment. That means for each variable that occurs in the benchmark, we need to keep track of a set of viable values, which we are doing with a set of intervals. And there's a way to extract forbidden intervals from constraints that are univariate to restrict these sets. And another, when we extend the assignment, we will reach conflicts at some point. So then we need to do conflict analysis and lemma learning. And for that, we combine several approaches. We can extract lemmas from intervals. We have some linearization lemmas to deal with nonlinear constraints. And we also introduce lemmas on demand in a model-based way. That is, I guess it's similar to the lazy approach from the previous talk for iAnd. And some techniques might return non-asserting lemmas. And in that case, we try some techniques to make it asserting, for example, literal subsumption. So bit vectors, I guess it was already introduced in the previous talk. They are machine integers of k bits, like U32 in Rust or uint32t in C++. But mathematically, it's the ring set modulo 2 to the k set. And you can, as numbers, you can typically interpret them in two ways. We have the standard unsigned interpretation, where all 1 bits, for 1 bits would be 15, and the signed interpretation, which is the 2's complement, where that would be -1. And compared to a full field, we have several pitfalls when we perform arithmetic. Obviously, the most common one would be the overflow. If we multiply two numbers, we are not guaranteed to have an increase because it wraps around. That also tells us we cannot perform the usual normalization of inequalities like you would do with integer solving. And we also have zero divisors. For example, 6 times 8 is 0 modulo 2 to the 4, which cannot happen in a field. But here we need to deal with it. So the bit vector language, I guess that's common knowledge after the previous talk. But let's go into more detail how we represent our constraints in PolySAT. So our bases are polynomials over bit vector variables, so multiplications and additions. And the base constraints are unsigned inequalities. Then we have the multiplicative overflow. So this omega star is supposed to be true if p times q overflows. For bitwise and structural constraints, we introduce new variables and represent them as an atomic constraint. And finally, we also need disjunctions of constraint literals, so negation and or, mostly for lemmas. So by reduction, we can also represent other constraints. For example, equality, P equals Q, is the same as if you have P minus Q less than or equals 0, because the domain is 0 from 2 to the k minus 1. That means it is equal to 0. Also signed inequalities, we translate them to unsigned inequalities by flipping the most significant bit. And quotient remainder, we represent this by introducing two new variables, Q and R, and then we can introduce these 5 auxiliary constraints. I'm not going into detail here. I'm just saying here we have the multiplicative overflow, which is an atomic constraint. This would be the addition overflow, but this is easily represented as a normal unsigned inequality, so we don't use a separate constraint type for that. Right, and here we have some clauses with more than one literal. So our method is based on MSTSAT by Leonardo De Muro and Dejan Jovanovic. And the basic idea is that we keep a partial assignment, and we keep assigning values to bit vector variables until we reach a conflict. And yeah, an important component is to keep track of these viable values. Terminology for the algorithm would be decision is when we guess the value for an unassigned variable where we have multiple choices. Propagation happens when a constraint is forced because only one remaining value is viable. A conflict is just the constraint is violated by the current assignment. Alternatively, if we somehow notice that there is no remaining viable value. Conflict analysis will learn a new constraint to avoid the conflict in the future. So let's just go through a simple example. We have these 3 constraints, which are polynomial equations, modulo 16, so 4 bits. In the first step, we could decide x equals x assigned to 0. That means under this assignment, the first constraint reduces to a univariate constraint. Since the coefficient of y is odd, it has an inverse, so we get a unique value for y, so we propagate y as 3. Similarly, the last constraint now reduces to a univariate constraint. We assign z is 2, and so on. But now C3 will lead to a conflict. Now we need to somehow resolve the conflict. We have the assignment. We saw that values for z and y were forced by the decision for x. So we need to revert at least this decision. And the naive way would just backtrack and choose the next value for x, but then we enumerate all assignments, which is obviously too slow if we have 256 bits. Yeah, better is we learn a new conflict to exclude this conflict, a new constraint to exclude this conflict, and ideally it should not just exclude this single assignment, but many conflicting assignments. So in this example, it is very simple. We can multiply the second equation by 2 times z. Then we subtract the second equation from the first one, and we get a nice new constraint, which we then add to the set of constraints. And in this example, we just backjump to level 0. We propagate a different value for x. Now we get immediately another conflict, but since we were on level 0, we cannot reassign any variables, so we now know that the formula is unsatisfiable. Okay, but in general, we cannot, we don't get some nice constraints from research simple operations. So we need some other techniques. But first, let's discuss how we keep track of viable values and how we choose values for decisions. So for each variable x, we keep a set of intervals. That is, we keep a set of intervals that are disallowed by some constraint for x. So, right. So Vx is represented as a set of intervals, and as we assign bit vector variables, you can think of it that we substitute a partial assignment, and some constraints become univariate. And for each univariate constraint, we try to extract some interval that cannot be assigned for this variable anymore. And we keep track of this set of intervals. And as a fallback, we also have bit blasting for these sets. However, it might sound counterintuitive since we want to get rid of bit blasting here, but if it's only about a single bit vector variable, it can still be helpful as a fallback. More details about the intervals. So we use the half-open intervals. We have a lower bound and upper bound. But what's different than usual intervals is that they may wrap around at the maximum value 2 to the k. So for example, modulo 16, interval 2 to 5 would have the values 2, 3, 4. The interval 13 to 2, however, would have 13, 14, 15, then it wraps around to 0 and 1. And if you have the same bounds, then we say it's the empty set because it's by convention. So there's this really nice paper by Stéphane Graham-Legrand, Dejan Jovanic, and Bruno Dutertre, where they introduced this notion of forbidden intervals. And I just want to briefly explain it with an example. If you have this partial assignment, x1 11, x2 13, and x3 9, and you have a constraint like this, you see that there is one variable y that is unassigned, and we can evaluate all the other terms. So in this case, if we substitute assignments, we get 11 is less than or equal 1 plus y. This means y cannot be in the interval 15 to 10, because if you add 15 here, we get 16, it wraps around to 0. And then all those values are infeasible until we reach 10 again, where we have 11 less than 11. So we add this interval to our set Vy to restrict the values for y. Okay. But a key idea is now that we can look at how we get these bounds. So this 15 was computed by negating this value 1. So it's from the term x1 squared, x3. And the upper bound 10 comes from this 11 minus 1. So from these terms x1 minus x1 squared, x3. So we can also extract a symbolic interval. So this y is not in this expression. Okay. Now in general, you have some constraint where you have polynomials PR, QS that are possible to evaluate in the current assignment M, and some variable x that is still unassigned. Now in the paper I just mentioned, they introduce, they have intervals for values where PQ are 0, 1, 1, 0, 1, 1. And they can also extract lemmas from these intervals. We have extended these intervals to coefficients where either both P and Q are the same, but not necessarily 1. And also where N and M are values different from 1 and 0. But in this case, you don't get a nice single interval, but you get a set of intervals. But you can compute it with a closed form formula. And also, yeah, what's new in our work is the combination with the value selection and the fallback to the bit blasting. And just as a short example, for the closed form formula, one of the cases looks like this, so it's kind of complicated, but it is still easily computable. But the idea is relatively easy, so I will just explain it with the help of this picture. So assume for a moment that these terms are over integers. Then this px plus r may represent a line like this. The qx plus s might be a steeper line like this. But then when we are in the, okay, so if we want to px plus r is less than qx plus s, then we know that the constraint can only be satisfied for x values in this interval. But now in the bit vector world, we can see there's a box like this where the computations wrap around. So instead of a line, we get several line segments. And then you see we have the interval from this intersection point to the wraparound point. And again here from the next intersection point to the next wraparound point. And we can then extract these intervals. And we do not need all those intervals because there can be a very large number. But we choose one based on the current model. Right, and now to briefly mention how we can use those forbidden intervals for conflict resolution. So we assume that the conflict is because we cannot assign a value to x without violating any of the intervals. So all those intervals are of a form like this. There is a constraint which implies that the variable x cannot be in the interval if some side conditions hold. So the idea is then, since no value for x is feasible anymore, those forbidden intervals must cover the domain, right? So now we want to use the symbolic representation of the intervals to extract a lemma for this. So what you can do here is, the idea from that paper is that you use the upper bounds for each intervals and say it must be contained in the next interval. And that you can represent like this. So for example, this u1 must be in the blue interval and so on. Right, in total the lemma looks like this. You have the constraints, the side conditions, and the linking constraints. And you might think what we do about this exists. Do we have another constraint? No, this can very easily be translated into a unsigned less than constraint. Okay, yes? Okay. Right, for example, we have seen a lemma like this during our experiments. These two constraints are the constraints where we got the intervals from, or the input constraints. And then we have two univariate constraints. You see both of these have set. Now the issue is if we add this lemma and we backtrack, then we do not have an asserting lemma because these two constraints are false from the input. Now we are left with a disjunction, and we cannot immediately use this to narrow the range for z. So, but what we can do is this first constraint is equivalent to z is 0. The second one, z is either 0 or 1. This can be done with the forbidden interval translation. And then we immediately notice that this first literal is subsumed by the second. So we can simplify the the lemma from 4 literals to 3, and now we get an asserting lemma. Right, and now I just want to show one more example, how we can use those linearization lemmas I mentioned earlier. So assume we have a input formula with these two constraints and possibly others, and we have reached a conflict with this zx greater yx, and some values for x, y, and z. Right, so what we can first notice, if we look at those values for x and y, those imply that x times y does not overflow. So we can add this constraint. Now we focus on these two, and they're justified by a tautology. By this tautology, we can now introduce this constraint and strengthen the conflict to only these 3 literals. So the lemma would then be this. Right, and then we jump back to x or y, and the last assignment will, since these two are from the input, this one must hold. The last assignment will be ruled out by this overflow constraint. Now we have a number of those lemmas, and the idea is that the trigger is when we have an inequality of a nonlinear variable in the conflict. The consequences of those lemmas are false in the current search state. Then we, for example, if you look at the last one, there is a variable r which doesn't appear on the left side. We find values for that by matching it against the search state. And driven by the benchmarks, we can add additional rules to that method to derive better conflicts. Right, so in total, we combine different methods for conflict resolution. So at first we have seen the polynomial superposition, which is nice when it works, but that's not very often the case. The forbidden intervals, they are very nice. If those don't apply, we use the saturation with the linearization lemmas. And since we have Boolean, since we have disjunctive lemmas, we also need Boolean resolution. And as a fallback, we can always backtrack, but that's obviously not ideal. Right, and I wish I could show you some benchmarks, but we are not there yet. So currently we have of those Satura benchmarks, we can solve one where Z3 gets stuck, and we have another benchmark where Z3 gets stuck, and our method can solve it. But yeah, so there's some progress to be made. PolySAT, in conclusion, it's a new bit vector solver for Z3. Instead of bit blasting, we do word level reasoning, and we focus on arithmetic rather than bitwise and structural constraints, although we do want to support them with the lemmas on demand. However, I think in the end, the results will be similar to the first experiment by Joni, where in the SMT-lib benchmarks, we don't expect to win, but rather on arithmetic-based benchmarks with large bit widths. Thanks, that's all from me.
I'll start with one. So how does your approach compare to existing MCSAT procedures?
So there is this this paper I mentioned with the forbidden intervals. They have however, I think they don't support nonlinear bit vectors at all, nonlinear terms at all. And also they use BDDs for the viable values. And we also tried that, but it turned out much too slow.
problem with
That's
with
why,
bits, yeah.
yes, that's why we changed to the interval-based representation.
Okay. Any other questions? If not, then let's thank the speaker again.